I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the law of conservation of momentum and drawing momentum bar charts. In this video, we're going to talk about the law of conservation of momentum and how we use momentum bar charts to represent the law of conservation of momentum. So first off, the law of conservation of momentum states that the total momenta of the objects before a collision is equal to the total momenta after that collision. Momenta is just the plural of momentum. So that means if we have multiple objects moving, we have multiple momenta. So here we have a situation where we have two spheres that are moving towards each other, different masses and different velocities. Those spheres' total momentum before the collision, taking into account that the sphere number 2 has a negative velocity, that means it's going to have a negative momentum. Remember, momentum is a vector quantity. So we would take the momentum of sphere 1 and we'd add the negative of sphere 2, and after the collision, they'd collide and move in this manner, and we could find the total momentum of both objects after the collision by multiplying mass times velocity, and again, taking into account that sphere 1 has a negative velocity and a negative momentum. So here are momentum bar charts and how we draw them. So some features of the momentum bar charts are that one, it has both positive and negative values. All objects with momentum in the initial situation are drawn in one column. That means you'd stack them on top of each other. So if we have a object that's moving in the positive direction with a momentum, say we have a height of 2, and then a second one moving in the same direction, we would stack it on top. If it's in the opposite direction, then we would draw it on the bottom. The positive values show that both objects moving in the same direction, and the negative value shows that it's moving in the opposite direction. Now, if there's no outside force or impulse, then that means the total momentum height, taking into account direction in the final situation, is going to equal the initial momentum height. So in this case, we have a height of positive 2 and negative 1, and that would be a total height of positive 1. So the momentum overall is going to be positive 1. In this case, when they're in the same direction, they end up with a overall larger momentum than when they were traveling in opposite directions. Now, the purpose of drawing momentum bar charts, like energy bar charts, is to visualize the conservation momentum, and then we're going to write an equation. So let's look at a couple of examples. So if we have two objects that are moving in the same direction, they collide and stick together, we want to find the velocity of those two objects as they move off together. So here's the situation. We have sphere 1 and sphere 2. We have the masses and we have the velocities of each of them, and they're both moving together in the same direction, and then they stick together after they collide and they move off as one object. So if we're going to draw our momentum bar chart, we know that sphere 1 has a momentum in the positive direction, and sphere 2 has a momentum in the positive direction as well. So sphere 1 and 2 have a combined momentum of 3 in terms of height. Now, what we know from forces is that when 1 hits 2, that it's going to slow down, but it's going to cause 2 to speed up. So that's why the difference in momentum. But what really matters is that they're stuck together so that we can actually just draw them as one object instead of drawing them as separate objects, because they're going to have the same speed. So now from that, we're going to write our conservation equation. The momentum of object 1 initial plus the momentum of object 2 in the initial is going to equal the combination of both of them together in the final. So now we substitute mass times velocity for each of those situations. So the two individual masses times their two individual velocities, those momenta added together, and that's going to equal the final momentum. And remember, it's mass 1 and 2, so we have to add the masses together to find the final velocity. After this, we can go ahead and rearrange this equation, and we can solve for the final velocity. And the final velocity is going to equal the sum of the initial momentum divided by the mass in the final situation. Then we can plug our numbers in, the values for initial velocities, and then do our calculations, and we get a final velocity of 0.625 meters per second. And this answer makes sense because we know when 1 hits 2, 1's going to slow down, from 1 to 0.625, and 2 is going to speed up to 0.625 from zero point 0.5 meters per second, and still moving in the same direction, so we have a positive velocity. Let's look at an example of a second situation. Now this one's, we have an object moving and collides with a stationary object, and the, the first object bounces back and moves in the opposite direction, as the speed of object 2 is what we are trying to find. So what we're going to do is we're going to draw a momentum bar chart. And here's the momentum of object 1. And object 2, well, doesn't have a momentum because the velocity is 0. Now, in the final situation, we know that object 1 bounces back. That's going to be a momentum in the opposite direction. So the final momentum of object 1 is going to be a negative value. So on the equation, we're going to subtract that value from our momentum from object 2. So now we know object 2, if the height in the initial situation was 2 and object 1 had a negative 1, well, we know that 3 plus negative 1 has to equal 2. So there's much more momentum for the object 2 than object 1 had initially, because object 1 bounces backwards. So now we have our conservation of momentum equation, that the initial momentum of object 1 equals the difference of the momentums in the final situation. So we can rearrange that equation and solve for the final momentum of object 2, which is what we're trying to find in terms of the velocity. Now we substitute the mass times velocity values for momentum, and then we can rearrange the equation to solve for the final velocity for object 2. So now we can substitute the values in for our masses and velocities, and then we do our calculations to solve for the velocity of object 2, and that velocity ends up being a half a meter per second. Now these two questions were quantitative values, but now what we're going to do is look at how you can use momentum bar charts to answer a qualitative situation. So the question is, which situation will ball 1 transfer more momentum to a stationary ball 2? Ball 1 moves towards ball 2 and collides with ball 2 and sticks together, or the situation where ball 1 moves towards ball 2 as the same velocity and then bounces off of ball 2 and it's now moving in the same direction as it was before. So which one's going to transfer more momentum? Well, how are we going to do this? Let's draw a momentum bar chart. So let's look at the situation where the two spheres stick together. So sphere 1 has a momentum, sphere 2 does not. In the final situation, we know that they're going to stick together. So that means the total momentum has to equal that height that we drew to begin with of 3. So let's just arbitrarily say that sphere 1 drops to 1 and sphere 2 has a momentum that is going to be larger because its mass is larger. So the total is going to be 3. So we can see the pink represents the change in momentum of ball 2 because ball 2 is now moving, whereas it wasn't before. So qualitatively speaking, we know that there was an increase in momentum for sphere 2. So now let's look and see what happens when they bounce off. We have the same initial momentum, but now we know that sphere 1 bounces off and moves in the opposite direction. So we draw a bar below. So we have a height of 3 in the initial, and now we have -1. So what do we have to do to show sphere 2 has a momentum that adds up to a whole total height of 3? Is we know that it has to be 4. And we're comparing the two pink values, and we can see that in the bounce off situation, sphere 2 has a much larger momentum than it did when the two spheres stuck together. So in the situation where an object bounces off, because it moves in the negative direction, there's going to be a larger transfer of momentum from object 1 to object 2 when it bounces off versus when they stick together and move off as one object. So to recap conservation of momentum, the first thing you do is you define the collision that occurs. This might be a cannon firing, a gun being fired, two cars colliding. In the case of what we were just looking at, we had two spheres colliding. It could be multiple objects. You could have 2, 3, 4, 5 objects that are colliding, and you just have to define the collision or force that is applied that causes a momentum to change. The second is we draw the initial situation for all objects with momentum, taking into account the direction of each object. As we take into account the direction, then we draw the post-collision momentum. If the objects stick together, we can draw one bar and treat them as two, or one object as with the combined masses. Then you write the conservation of momentum equation with the pre-collision momentum equaling the post-collision momentum. And don't forget to take into account direction. I've mentioned this many times because this is a very common mistake as we forget to take into account direction. And then the last step is to solve the equation for what is being asked or analyze the bar chart qualitatively as we did in example 3 to answer the question. This is an introduction to conservation of momentum and how to use momentum bar charts to solve for those. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.